Today we will finish the discussion on IR models, which captures the way the information need is satisfied for the user by the web or the information repository. We will also explore the relationship between NLP and IR. After all, we are discussing information retrieval in the context of natural language processing, exploring the question of how NLP and IR interact with each other, how the two fields can benefit from each other's strengths. So, we continue first of all with the question of IR model, where the main question is how the information of the information repository, internet being a special case of this repository, is represented to the user to satisfy his or her information need. So, we continue with the presentation. We have seen this before, that an information retrieval model is defined as a quadruple, where the four components are D, Q, F and R being a function of Q I and Dj, where Q I is the ith query, Dj is the jth document. Now, D, the first component of the tuple, is the set of documents, Q is the set of queries, F is the framework for modeling the document, query and the relationship. So, for example, will the document and query be represented as vectors of numbers. So, that question comes under the purview of F. R is the ranking function, which returns a real number expressing the relevance of the document Dj with the query Qi. So, this was discussed before, and we also then talked about how the importance of the index terms is represented by weights associated with them. So, suppose T is the number of index terms in the system, which comes from the vocabulary of the corpus being searched. So, suppose there are D documents in the corpus, we collect all the important terms in these D documents, and suppose that those number of terms be T, then K, the set of index terms K1, K2, K3 up to K small t, is providing the index terms. Ki is a particular index term, Dj is a particular document small dj, Wij is a weight associated with Ki and Dj. So, Ki comma Dj, this tuple is a combination which shows the importance of the keyword Ki in the document Dj. Wij equal to 0 indicates that the term does not belong to the document. So, in particular, if we stick to a Boolean situation where the weight value is 1 or 0 expressing presence or absence of a keyword in the document, then this is a particular way of assigning weights to the terms. This is the first starting point of presenting the weight of terms in the information retrieval scenario. Wij equal to 0 indicates that the term does not belong to the document. Vec Dj is nothing but a vector of weight values of the keywords K1 to Kt with respect to the document Dj. So, W1j, W2j up to Wtj are the weights of the keywords K1 up to Kt in the document Dj. That is why this double lower suffix 1j, 2j and so on. Gi vec Dj is equal to Wij This is a function which returns the weight associated with the pair k I d j. So, this is a function which extracts the weight of the keyword I with respect to the document j. So, this is a precise formulation of the classical information retrieval model, where the world consists of the keywords, a document, and the weightages of these keywords with respect to the document. Proceeding further, we now go into different models of information retrieval. The first model is the Boolean model. We touched upon this last time. Let us explain this more clearly. This is a simple model based on set theory, and it allows only and, or, and not operations. So, queries are specified as Boolean expressions. They have a very precise semantics and the formalism is neat. So, what do we mean by this? The semantics is precise means that the meaning of the query is well understood in terms of presence or absence. So, if we say the query is T1 and T2 and not of T3, suppose we say this, okay, and in that case the meaning is very clear. The meaning is that give me a document which contains the keyword K1, contains the keyword K2 and does not contain the word K3. All right. So, this is the meaning of the statement here, that the Boolean model gives rise to precise semantics. The formalism is neat. We simply have the and, or, and not operators, and the propositions, so to say, are the presence or absence of the keywords. Thus, Wij is either 0 or 1. So, now if I take this query q, which is Ka and Kb or not Kc. So, this was discussed last time. We can convert this query into a disjunctive normal form. So, this whole expression is equivalent to Ka and Kb and Kc, or K and Kb and not Kc, or Ka and not Kb and not Kc. So, this can be very easily seen from the query expression Ka and Kb or not Kc. So, 110 is a conjunctive component in the DNF expression for the query. Now, we can picturize the query as follows. So, it is as if Ka, the first keyword, has a region of influence shown as the blue circle, Kb has a region of influence, and Kc again has a region of influence. So, this area where these regions of influence intersect indicates the presence of all Ka, Kb and Kc, all the three are present. So, that is why this conjunctive component 111 belongs to this intersection area. This is the area which contains Ka and Kb, but not Kc. Similarly, this is the area which contains Ka, but not Kb and Kc. So, this set Venn diagram kind of picture expresses the conjunctive components very well. Now, we say that the similarity of a query q and dj is 1. A particular query q has similarity of 1 with dj if there exists a conjunctive component of the query such that this conjunctive component belongs to the DNF expression for the query, and every weight component of the vector for the document matches the weight component of the query vector. That means, each component of the query vector, each component of a conjunctive component of a query vector matches the components of the document vector. This is the meaning. So, simply put, this means that the presence or absence of keywords in the query should be matching the presence or absence of the keywords in the document dj. Then we say that the similarity is 1. Or more simply put, this only means that the keywords which are present or absent in the query are also present or absent in the document. Then that particular document has similarity value of 1 with respect to this particular query. Now, the drawbacks of the Boolean model are the following. Retrieval is based on binary decision criteria with no notion of partial matching. So, all keywords which are present or absent in the query also have to be present or absent in the document. This is a black and white situation. Users information need is never this way. Users information need is often fuzzy, and the user is satisfied with fuzzy information. No ranking of the documents is provided because the score is simply a similarity value, which is either 0 or 1. All documents which match the query term presence or absence have value either 1 or 0. There is no relative ranking between the documents. So, this is also not a realistic situation because we know documents supply the information need of the user in different degree. Some documents are more relevant, others are less relevant. So, by its very nature the problem is fuzzy. It is not a black and white situation. It is not a 0-1 situation. Information need has to be translated into a Boolean expression, which most users find awkward. So, one can immediately see that in the Boolean model of information retrieval, there is an artificiality. Okay. What the system is doing is that it is simply matching the keyword presence or absence in the query with the keyword presence or absence in the document. Now, the users have information need. When the information need arises in the mind, it is never in the form of presence or absence of keywords in a document. Okay. It is hardly the case that the user is trying to express his information in terms of presence or absence. The user is not saying that give me a document which contains the term Delhi, but not the term Qutub Minar. Okay. This is never the case. It is very artificial. The user might say give me all those information about Delhi which does not mention Qutub Minar or which is independent of Qutub Minar. Give me all those facts about Delhi, but do not tell me anything about Qutub Minar. So, user's information need is expressed that way. So, user is not thinking of a particular document, user is thinking about information. So, this information has to come from the information repository. So, therefore, we are saying that the Boolean expression formulation is found to be quite awkward by users. The Boolean queries are formulated by the users, and many times they are too simplistic. This is because we have said that users information need is much more complex than simple term presence or absence. Many times it is very fuzzy, many times it is imprecise, full of noise. So, Boolean model being a 0-1 world cannot capture this situation. So, as a consequence, the Boolean model frequently returns either too few or too many documents in response to a user query. So, this is a fact that the Boolean model, because of its insistence on strong 0-1 matching, would either return too few or too many documents. Okay. So, all those disadvantages of course exist for the Boolean model, but it has its own advantage also. First of all, there is no doubt about the fact that information need begins or starts getting satisfied from the notion of presence or absence of keywords. So, presence or absence of keywords is very important. It is true that if a term is present in a document, the document may not necessarily pertain to that particular term. Similarly, if a term is absent from the document, it may not necessarily be the fact that the document does not say anything about that term. Okay. Both the possibilities exist, but still Boolean model of information retrieval provides a basic platform for information retrieval. It provides a sanity check for the search engine which is being developed. The search engine should at least capture the situations where the terms are present or absent in the document. Okay. It should be able to, it should have at least that capability. So, it is like a sanity check. So, we move to the next model of information retrieval, which is probably the most popular model, and practical search engines do use this particular model known as the vector model. So, use of binary weights is too limiting. Non-binary weights provide consideration for partial matches, and these term weights are used to compute a degree of similarity between a query and a document. So, this is very important. Degree of similarity is important because we have a human being making queries to the web. It is the information need of a human being which is being satisfied, and human beings by nature are fuzzy, noisy, imprecise. Ranked set of documents provide for better matching. So, here comes the notion of ranking, which is fundamental to information retrieval, and it is this particular fact, the need to have very precise ranking whereby relevant documents are captured, that leads to the exploration of CAN. Language insights, can natural language processing be integrated with information retrieval. This is the genesis of studying NLP's influence on IR and IR's influence on NLP. The vector model is as follows. We have already defined the document, query, the framework, and a relevance function gives us the information retrieval model. Now, the weights Wij is greater than 0 whenever Ki belongs to Dj. Wiq is greater than or equal to 0, which is associated with the pair Ki and Q. Now, the vector representation of the document Dj is W1j, W2j up to Wtj. So, this is with respect to the keywords 1 to t for the document j, and similarly the vector of q is W1q, W2q up to Wtq, which is nothing but the weightages of the keywords in the query. So, in this space queries and documents are represented as weighted vectors. So, the similarity measure is typically the cosine similarity measure. The similarity between the query q and document dj is the cosine of the angle between the vector for q and the vector for dj. So, this is computed as vector for dj dot vector for q, the dot product, divided by the mod of dj and the mod of q, because we know that the dot product is nothing but the product of the magnitude of the vectors and the cos of the angle between them. So, this particular expression gives us the cos of the angle between the two vectors. Now, the vector the dot product can be found from the sum of the product of the weight values, okay, with I varying from 1 to t, where t is the number of keywords, and it is divided by the modulus of dj vector and q vector. So, similarity because of this formulation is between 0 and 1. A document is retrieved even if it matches the query terms only partially. So, this is the crucial difference from the Boolean model of information retrieval. Even if the query terms partially match, we would retrieve the document and show it to the user. Of course, the rank could be lower than a document which matches the information need exactly. So, similarity is expressed as this product of weightage terms, corresponding terms, divided by modulus of dj and modulus of dq, modulus of dj and q, this product. Now, the question is, how do we compute the weights wij and wiq? So, a good weightage scheme must take into account these two effects: quantification of intra-document contents, which is the similarity. So, this is the TF factor, the term frequency within a document, and quantification of inter-document separation. This is the dissimilarity, and this is known as the IDF factor, the inverse document frequency. So, what is being said is that this is what is being said. Bit of writing will make it clear. So, suppose we have two documents D1 and D2. The vector for D1 is W11, W12, sorry, W21. The second suffix is the document suffix, W31 up to WT1, okay, corresponding to T keywords. And for document 2, it is W12, W22, W32 up to WT2. Okay, we have these two documents. Now, the weightage should be such that if the documents are similar to each other, then the weight should capture that similarity, and if the documents are distinct from each other, their contents are very different, that also should be captured by this weighting scheme. So, you see this is a very important point: weight such that similar documents are I will continue to the second page. Similar documents are considered similar and dissimilar documents are indeed dissimilar. So, this is the responsibility on the weightage scheme. The weight values would be such that documents which are similar are close together, documents which are dissimilar are far from each other. Okay, so, the slide expresses this factor and says that there is something called TF factor, which captures intra-document content similarity, and there is this IDF factor which achieves inter-document separation, and the weightage is equal to term frequency of ij into inverse document frequency of I. So, here TFij means the term frequency of keyword I in the jth document. How many times does the keyword I appear in the jth document, and IDF of the keyword I, this will be defined shortly. So, here we explain these terms. Suppose n is the total number of documents in the collection, and ni is the number of documents which contain ki. Okay. The particular keyword ki is contained in ni documents. fric ij is the raw frequency of ki within dj. Okay, so, this is the term frequency of the keyword ki within dj. It is equal to the number of times the keyword ki appears in the document dj. So, a normalized TF factor is given as f ij equal to frequency of ij divided by max over L of frequency Lj. What does it mean? It means that take that term whose frequency is maximum in the jth document. Take that frequency. Let that divide the frequency of the ith keyword in the jth document. So, that would give a normalized TF factor of the ith keyword in the jth document. And this maximum is computed over all terms which occur within the document dj. The IDF factor is computed as IDF I equal to log of capital N divided by Ni. So, Ni we remember is the number of documents which contain the keyword Ki, and capital N is the total number of documents in the collection. So, N by small ni is the inverse of the proportion of the documents which contain the keyword Ki. So, log is used to make the values of TF and IDF comparable. It also can be interpreted as the amount of information associated with the term Ki. Okay. So, small ni by capital N would be something like a probability. So, this term is like negative log of probability, which is something like the entropy, and entropy is related to the information content of the document. So, this is IDFI. Now, you should verify that IDF is indeed a factor which distinguishes one document from another because of a particular keyword Ki. In particular, look at the boundary conditions. If Ni equal to capital N, that means if a particular word or a particular keyword appears in all documents, then this, by virtue of this keyword, we will not be able to distinguish between documents. Okay. So, this particular word is not specific to a particular document, and therefore, log of 1 will be equal to 0. So, IDF of this ith keyword is equal to 0, and since the weight value contains IDF as a product component, the weight value will become equal to 0. So, the meaning of this is that the weight value of a term of a keyword which appears in all documents is equal to 0. If we take the other extreme, that is the keyword appears in a very small number of documents, then this tends to be large. So, log of this number would be smaller, but even then it will be large value. That means, keywords which appear in sparse number of documents, small number of documents, have high distinguishing power. So, once you give that particular term in the query, a particular document or two documents at most would come out, and therefore, these have very high information content, okay, and therefore, their weightages also will be high. So, this is the way the weightage scheme is decided for a document vector, and it makes lot of sense. So, the best term weighting schemes use weights which are given by product of the term frequency and the inverse document frequency. This particular strategy is known as TF-IDF weighting scheme. For the query term weights, a suggestion is that we take the IDF factor, of course, we also take the term frequency, but we have a multiplying factor of 0.5. This is the normalized term frequency, we multiply it by 0.5, we also add 0.5. So, all these are actually empirically decided. It is found to be a good formulation of the weightage of a term in the query, and that comes from the fact that the query is typically very small. It is a document, quote unquote document, with a small number of terms, and therefore we have to see how to weight the terms in the query. Also, it is not clear how to get the IDF value of a query term with respect to the queries. So, that is why this kind of empirical formulation is used. The vector model with TF IDF weights is a good ranking strategy with general collections. The vector model is usually as good as the known ranking alternatives. It is also simple and fast to compute. So, over the years, through many implementations, through the engineering experiences, it has been found that the vector model really delivers the goods. It brings up in the list the relevant documents, and hence systems have continued with the vector model. We explore this model further. The advantages of the vector model are: term weighting improves quality of the answer set, partial matching allows retrieval of documents that approximate the query conditions, cosine ranking formula sorts documents according to the degree of similarity to the query, and the disadvantage is that it assumes independence of the index terms. So, this is a fact that the terms are given weightage independent of their context. So, the weight of a term is simply obtained from its frequency in the document and its IDF value. This is how the weight is calculated, but it is not clear that it is a bad decision. It is delivering the goods. Now, we take an example to understand the vector model, the effect of the weightage. So, here is a Venn diagram like picture. There are 3 keywords K1, K2 and K3. The blue circle shows that in the circle of K1 there are D2, D6, D5, D1 and D4. So, this means that these documents D1, D2, D4, D5 and D6 contain the keyword K1. Similarly, this red circle shows that the documents D3, D5, D6 and D7 contain the keyword K2, and this light blue circle shows that the keyword K3 is contained in D3, D1 and D5. A table represents this fact. Document D1 is represented as 1, 0 and 1. We are giving a Boolean representation for the documents. So, K1 is present, K2 is absent, K3 is present in document D1. This is the case. D1 you see is in the intersection of K1 and K3. Similarly, D2 we can see from here, D2 is only in the region of K1, it contains neither K2 nor K3. So, D2 is 1, 0, 0. D3 is shown as 0, 1, 1 because D3 is in the intersection of K2 and K3, K1 does not appear there. So, 0, 1, 1. Similarly, we have D4 which is 1, 0, 0, D5 is 1, 1, 1. Why is D5 1, 1, 1? Because D5 is at the intersection of K1, K2 and K3. D6 is 1, 1, 0, D7 is 0, 1, 0. And query contains, let us say, all the keywords K1, K2 and K3. Now, if we take a dot product of Q and Dj and the dividing factor which is weightage which is the modulus of Q and modulus of Dj, that is same for all of them. So, that will not change the score of the documents. So, here we are taking the dot product of Q and Dj, 1, 1, 1, D1 score will be 2, D2 score will be 1, 1, 0, 0 and 1, 1, 1, dot product is 1, D3 score will be 2, D4 score is 1, D5 score is 3, D6 score is 2 and D7 score is 1. Now, you can see that this particular scoring for this kind of vector creation is intuitive. D5 should indeed have a high score because all the keywords are present in this, and D6 and D1 should have similar score because each of them contains 2 out of 3 keywords. So, let us see, D1 score is 2, D6 score is also 2. D2 and D4 again should have same score of 1 because only one keyword K1 is present in this, and that is the case. So, you see, if you simply go by term presence or absence, then D5 must be the winning document, which is the case. Now, we change the weightages in the query. Okay, the document vectors are not changed. So, they simply express term presence or absence. However, the term weightages are changed in the query. We say that K 3 has a weightage of 3, K 2 has a weightage of 2, K 1 has a weightage of 1. So, K 1 may be present, but its weightage is smallest. So, when that happens, what we find is that the score for D 1 is 4, score for D 2 is 1, score for D 3 is 5, score for D 4 is 1, score for D 5 is 6, score for D 6 is 3, score for D 7 is 2. So, D 5 is again the winner, because all keywords are present in this and their weightage gets added. However, we see a rearrangement of documents of other documents. So, D 1 and D 6 had equal score in the last weighting scheme of 1 0. Here we see that D 1 and D 6 have different score. D 1's score has become higher because it contains a high weightage term K 3. Moving further, if we now have weightages reflected in the documents also. So, in document D 1, K 1's weightage is 2, in document D 4, K 1's weightage is D 4, in D 5 its weightage is only 1, it is just present without any weight modification. Similarly, K 3 has weightage of 1 in D 1, 3 in D 3, 4 in D 5 and so on. Again we see D 5 is the winning document, but D 1 and D 6 score have now become same. D 7, which was nowhere before, has got a high score now and is beating D 2 and D 6. So, this is the effect that the terms have when they are weighted. When the terms are weighted, the picture changes very dramatically. Just term presence or absence gives one kind of score for the documents. Okay. However, when their weightages are changed, then they may show a completely different picture. Documents which are high up in the list can go down and other documents can rise up. And this should be the case because different keywords have different weightages in the document, and this should be reflected. And this also captures the fact that the documents and queries should reflect the weightage of the terms, leading to different relevance values. Now, the key question that arises is that if the weightage is so important and it changes the ranking of the documents quite dramatically, how do the weightages come? Where do they come from? So, we take information of the document, information of the whole corpus, the knowledge of the world, the knowledge of the domain from where the documents come, and then the weightages are formulated. So, this is an engineering problem. This is a problem which requires understanding the problem very well. So, now we go back to our discussion of NLP and IR. So, once we know that IR is looking for solutions to the problem of term weighting, okay, that is the crucial point, term weighting. The better the term weighting, the better is the retrieval, and we will see that there is another factor, query refinement, query expansion. This also has a role in the information retrieval scenario. Now, weightages of the term can come from natural language processing considerations. So, we go back to our discussion of the relationship between natural language processing and information retrieval, NLP and IR relationships. First question is how natural language processing has used information retrieval. NLP has used IR in the following way. Web is looked upon as a huge repository of evidence for language phenomena. Web is full of text, there are lots of corpora, utterances of people, writings of writers, writings of common men, writings of people from different languages, different backgrounds. So, web is a very rich repository of language phenomena. Now, there is a very effective measure called pointwise mutual information, which has been used for many very fundamental NLP issues like co-occurrence, co-location, etc., and also applications like malapropism detection, evaluation of scene sets. So, this PMI measure is obtained against the corpus on the web. A very famous idea, namely page rank, has been used for words-and disambiguation. Page rank came from information retrieval literature. It has been made famous by information retrieval, and page rank like ideas have found application at many places. In particular, words-and disambiguation algorithm in unsupervised setting has made use of page rank. Of late, there has been a lot of interest in generating probabilistic dictionaries from comparable corpora which abound in the web, and this is recent work. So, again natural language processing systems have benefited from web and IR in the sense of getting probabilistic dictionary. This research is on, of course. And in turn, how has information retrieval used natural language processing? So, it has IR has always been concerned with query disambiguation. Query words are typically polysemous. When we do only term based matching and ignore synonyms, then we have low recall. If you are not careful about polysemy, then it leads to topic drift and lower precision. So, disambiguation is important in information retrieval. However, the techniques are very different from natural language processing, because the context is very small in query disambiguation. So, the field has used pseudo relevance feedback. We will have to discuss this issue little later. Another important basic question which has existed in information retrieval is whether morphology should be or should not be done. Is it better than statistical stemmer? Now, languages which are morphologically strong, rich, it seems they need strong morphological processing. So, morphology processing is a very NLP concern, and statistical stemmer has been the invention of information retrieval. So, do they come together? Can we do without elaborate morphology processing is a question to be answered. But yes, information retrieval has benefited from the morphology analysis, which linguistics and NLP has contributed to the field. The other point is something we mentioned a few minutes back. Term relationships have to be captured, term weightages have to be captured. This is a central concern in IR, and one sees two kinds of work in this area: random walk and lexical semantic association or indexing. So, both of these would be discussed. If we look at this problem of words and disambiguation using random walk, then the problem is as follows. We have the words in a sentence, and what happens is that on each word we erect a column of senses. Okay. So, bell has 3 senses, 1, 2, 3, a hollow device made of metal that makes a ringing sound when struck, a push button at an outer door that gives a ringing or buzzing signal when pushed, the sound of a bell. So, these senses are erected on the word bell. Similarly, ring, church and Sunday, all of them have senses shown. So, then after that these senses are linked by arcs, and from each stage to the next stage there is complete connection. The weightages are as per the Lec similarity measure. Find out the overlap of words in the glosses and example sentences of these senses, and thereby create a graph. After that, one runs this page rank algorithm, and the scores get updated at every iteration using this formula, which we are not detailing out now. Essentially, the idea is that every node has an importance imparted to it by the weightages on the arcs which descend on these nodes, and then from these nodes the importance gets transferred to other nodes. So, this is the way the nodes transfer importance from one stage to another, and finally winner nodes emerge at every column of senses. So, this is the random walk algorithm, this is also the page rank algorithm, and these ideas came from information retrieval, word sense disambiguation algorithm of Rada Mihalcea, which works on unsupervised corpora, unmarked corpora, unsense marked corpora, or the setting is unsupervised learning with only WordNet as the resource that produces results of sense disambiguation. There is another very interesting problem where NLP has made use of information retrieval, and this problem I describe as malapropism and its processing. So, this problem has become important in correcting errors in text which are semantic in nature. So, if there are spelling errors, they can be corrected. If there are syntactic errors, then there are systems which do grammar check and come up with suggestions, or at least show that something is wrong grammatically with the sentence. But words which are spelled correctly, but are semantically odd, do not fit in the semantics of the context, they are harder to detect. So, we will discuss this problem in the next lecture.